Next talk is from Matthew Treinish, who is going to be talking about Tempest and the OpenStack integration testing. He works for HP and is the project lead for the quality assurance program of OpenStack. Please welcome Matthew.
Okay, well, as Josh said, I'm here to talk to you about Tempest, which is the biggest project in the quality assurance program in Tempest, or OpenStack. So let me just get started. So I'm sure everyone's seen this, this diagram before. Everyone's favorite. It's the complicated view of how OpenStack works internally. And this is also severely out of date because it's from Grizzly. We're currently working on Juno, so it's missing a bunch of services and a bunch of projects. But the end message is that OpenStack is complicated. And because it's complicated, it's also very complicated to test it to make sure it's working properly. Before we had Tempest, every project, which was the bigger box on that previous slide, had its own unit tests. Some of the projects also had functional tests where they would spin up their respective stack and poke it in some way and make sure things were working properly. But there was nothing testing that whole picture together. There was no guarantee that Nova would talk to glance properly if you wanted the two pieces to work together, which is really what OpenStack is building. It's about building infrastructure as a service ecosystem with a bunch of projects that work together. And we didn't have a way to test that. So that's where Tempest came in. Tempest was designed to be the official OpenStack integration test suite. It only deals with black box testing through the OpenStack REST APIs. That's by design, because if you remember the diagram, actually go back to that, the dashed lines are REST APIs and everything else is internal communication. So we only deal with the dashed lines there from the external perspective. If we started worrying about the internal details, things would get far too complicated and it would be almost impossible to verify. Currently, Tempest has over 2,300 tests, which cover every current incubated and integrated OpenStack project. I think that number is now actually closer to 2,800. I made these slides about 2 months ago. And it's also used as the gating tests for every integrated OpenStack project, which means that if you submit a patch to any OpenStack project, Tempest is going to run against it at least 2 times. I think we aim for about 4 per patch, but it's at least twice. So Tempest was started late in the Diablo cycle to solve the problem of not having an integrated test suite and no way to test the complete OpenStack picture. 2 cycles later in Folsom, we started gating on every commit of Tempest, which means we spun up OpenStack using DevStack, and we would use Tempest against that deployed OpenStack. And as of the Icehouse cycle, it was one of the 5 most active projects in OpenStack by both code commit count and review count. I think it was number 4 for both, actually. And it's become so important that TC has dictated that every project that wants to be integrated has to have Tempest tests before that can happen. And the Foundation board has also stated that Tempest will be used for whatever they decide dev core validation is. And that's always up for debate. But so Tempest has become increasingly more important. And the graph on the bottom just shows the growth rate and activity in the Tempest project. And you can see that it's almost exponential for some of them. The number of tests, I think it's the square blue. That one looks almost exponential. So Tempest has been growing very rapidly. It hasn't been around that long, and it's become increasingly important. And with that growth, there have been some growing pains. The biggest one is that we have a huge number of new tests, and we also have a huge number of new projects. OpenStack is growing very quickly, and integrated test suite has to grow equally as quickly to keep up with all of the changes, otherwise things aren't being tested. Another thing is that all the common code that we have in Tempest to handle things like REST API communication and other like version discovery stuff, has gotten increasingly more complicated as we start adding more APIs. And we have to be able to handle all of that. With the number of tests we have in Tempest, another thing is that individual test management becomes increasingly difficult. If we're running 2,300 tests every time we run Tempest, how do we figure out that one test didn't run because of configuration mistake? It got skipped instead. When you're looking at the output of 2,300, it's hard to see one skip that changed from this run versus the run 2 days ago. Things like that. Another thing is, as the number of tests grows, we have to get more and more clever about how long it takes Tempest to run. The current goal we have is to keep it running in under an hour with a DevStack deployment in the gate. As we start handling more services, more APIs, more options, the configuration for Tempest gets increasingly more complex. For example, right now in Tempest, I think we have over 250 configuration options to try to handle all the potential options that OpenStack can get deployed with. So from those growing pains, we decided to have some design principles to define what Tempest is. Because before we had this, we were kind of just doing everything the way we wanted to. There was no order, and Tempest was kind of a mess. So we decided to define what Tempest was and how we were going to do integrated testing in OpenStack and go from there. So the first one is that Tempest should run against any OpenStack cloud, whether that be DevStack or someone's public cloud deployment. It's an ideal goal. Unfortunately, because we run it only in the gate for verification, there's a bias for running towards DevStack. We don't get feedback from people who run it against large deployments on a regular basis, so we don't know where we screw up and have a hard-coded DevStack default, for example. Another principle with Tempest is everything explicit. This came out of auto-discovery, so Tempest APIs provide a certain level of discovery of features. And when we started doing that in the gate, things would get skipped and we wouldn't realize it because the discovery APIs were broken. And that's not really good testing if you're trying to test an API and it says it's not enabled, but it really is, and you skip it instead of failing. So we came up with everything explicit, which means if you want to test something, you have to say, this is enabled, so make sure you test it. And we carry that philosophy throughout the code in the testing as well. We don't make any underlying assumptions, or we assume that everything from the API is garbage and we have to verify it manually. And that's actually worked pretty well for keeping the quality of the OpenStack APIs high. The other thing is we should only be using public interfaces. This comes back to the black box testing. At one point, there were white box tests which would make an API call and then check the node database layer to make sure that something got put into the database. And that's completely unmaintainable when you look at the scope of OpenStack, the scope of what we're trying to test with Tempest. So we decided that everything has to be through a public interface and has to be queryable through the public interface if we want to test it. And if you can't do that, then the API is broken, because it's also broken for end users who want to do the same thing. It should be a self-cleaning test, because we're creating resources a lot for these tests. So a Nova API test, for example, will create a server, do something to the server, and at the end it has to make sure it deletes the server and it doesn't leave it dangling around. And this comes back to the first design point of working against any OpenStack cloud. And if you're running Tempest against a public cloud, you don't want it to be sitting there eating resources that aren't deleted. We try to do a good job of that. Sometimes we have bugs that slip through and resources get left dangling. It's a constant problem. And the other thing is it has to be self-testing, which is something that came out of one of the growing pains on the previous slide, increased common code complexity. When things started getting very complicated, we realized we weren't actually validating Tempest itself work like we expected it to, and we found a lot of bugs. So we started implementing unit tests to fix that. So this slide outlines the basic Tempest architecture. It's a pretty cheap and simple diagram, but it outlines that there are 4 basic types of testing we have in Tempest. We have API tests, which use a Tempest-specific common REST client with service client implementations for all of the OpenStack services and APIs. So there's a Nova Servers client, a Nova Flavors client, for example, a Neutron client, and so on and so forth. But they're all based on the same common REST client, and they're just extensions on it, which has been very handy because it lets us write tests in a very uniform manner between the services for validating the APIs. Then we have two classes of tests which use the official Python clients to go over the REST API, and we also have Nova's EC2 implementation. Since that's published in OpenStack, we test that as well, but we use Bodo instead of testing the API directly, which is why we have the common REST client, because something we found is that Python clients often mask bugs and code around them. If there's a bug in the API, instead of fixing it in the API layer, they fix it in the client. And we didn't want that to fail tests. We wanted to fail test if the API is broken and not work around them. So the first class of tests we have in Tempest are the API tests. They directly test the OpenStack REST APIs for all the services, both the admin and regular user APIs. And, they use the unified Tempest REST client, which is a simple wrapper around HTTP lib 2, and adds some fancy testing features like fast raising exceptions if it's an error code that's not expected, and some other things like adding keystone auth based into it. And then there are two categories of API tests, positive and negative tests, which is, it's a little weird, but a positive test is something that you expect to basically return a 200 response code. It's something that you expect to succeed, like create a server in this tenant and make sure you can do something with it. While the negative test is something you expect to fail and you expect to get an exception from. An example of that would be create a tenant with an invalid name or something. You expect a failure to come from it. The issue we had with negative testing was that the negative space is basically infinite, if you think about it. You have a defined behavior for good API requests, then anything that's different from that, which could be anything, is a valid negative test. And what we started seeing was there was a slew of developers right before the Hong Kong summit that just started pushing like one-line negative API tests that said like, oh, you didn't test this with an asterisk in the API request, and that's an invalid character for that call. And we started getting hundreds of those. So we decided to switch that to use test scenarios and the API schema to auto-generate the negative tests. So we have a defined spec for what the API good behavior is, and then we auto-generate what the bad stuff is based on that good spec. And it gives us predefined negative testing characteristics. And we won't catch everything that way, but at least this way we don't have a slew of junior developers who want to get OpenStack patches by pushing online changes that send random characters to random endpoints. The next type of testing are the scenario tests. Scenario tests are a little bit more involved. They're designed to simulate end-user workflow. Basically simulate like what a user would do if they wanted to use a server with Cinder and do something with that Cinder volume and migrate it to a new server. They currently are using the Python official clients, although right now we're actually working on removing that and switching to the Tempest clients, because the Python clients, when they fail, it's almost impossible to figure out why it fails sometimes. And they also do too much under the covers, so we're switching that to Tempest clients. But the original intent was, since it's end-user workflows that we're trying to simulate, we should use the official clients because that's what end users are going to do. The obvious implication of that is that end users shouldn't be using the official clients because they're broken, but I'm not going to draw that conclusion for everyone. And ideally, these tests will only be used to test integration points between projects. Like I mentioned, the Cinder and Node example, where you boot a server, create a Cinder volume, attach it, do something to the Cinder volume, go on from there. We don't want these tests to be basically mirrors of the API tests. The API tests are testing singular API functions, like create a server with this and this option. Scenario tests are more for create a server, do something with the server like a user would. It's kind of a weird distinction. We get gray areas all the time, but so it is. The next category of testing are the command line interface tests, which test the official client command line interfaces, and it's really just a quick sanity check of the functionality of command line interfaces to make sure they behave as expected. They only perform read-only operations, and they're very simple. And it was mostly added to Tempest for gating convenience. When we added this, I think it was about 3 cycles ago, there wasn't an easy way to spin up dev stack nodes in the gate, and we didn't have a way of functionally testing the Python client's command line interfaces very easily. So we just dumped it in Tempest because it already had all of that set up in there. But if you remember from the earlier slides about the design point, Tempest is all about the REST API, not the command line interfaces of the clients or the Python APIs of the clients. So this really doesn't fit the mission of Tempest, and one of the goals for this development cycle is actually removing the CLI tests and putting them back in the Python clients as functional test jobs, now that we have the ability to easily spin up this for gating purposes, which was the only reason we put it in Tempest in the first place. There's also a stress test suite built into Tempest. It uses the Tempest tests to generate load by basically running the tests in a big loop, and it also runs them in parallel. It's configurable on how you're running the tests. There's a set of dedicated scenarios for generating stress on the cloud. They're mostly like just creating a set of volumes or a set of servers in big series. And then there's also the ability to decorate any existing Tempest test to be a stress test generator. Because a lot of the things we're doing in Tempest, you do it once, it's a good test. You do it 50 times at once over the period of an hour, it's a good way to actually stress your cloud. So we added the ability to make any Tempest test a stress test. All the scenario tests that I mentioned previously, they're good stress tests because they're testing integration points and they're doing lots of things. So if you run them a lot at the same time, that's a good way to stress your cloud. And the stress tests, the way you run them is configurable, but it's basically you set a period of time to run for, and then you say, do you want to run these tests serially or parallelly, how many threads, and it just loops until time runs out or everything explodes, which happens sometimes. And then there are 2 other classes of tests in Tempest. There are third-party tests, which often gets confused by people trying to spin up third-party CI. It has nothing to do with continuous integration. It's about testing the EC2 API in Nova. We called it third-party tests because we assumed that one day there could possibly be another non-OpenStack API in an OpenStack project. Because the theory is if you have an API in your OpenStack tree, or in your OpenStack project tree, it needs to be tested because it's a published API. And since Nova does that with EC2, we have to verify that EC2 works. I don't actually ever see that growing because all the other third-party APIs have been spun off as wrapper layers outside of the project, like a StackForge project. The other thing is unit tests, which are basically as they sound. If you remember from the growing pains, we figured out that one of the issues was we didn't actually have any verification that Tempest was doing what we thought it would do. So back in Havana, I actually pushed a bug into the Tempest tree, which broke the wrapper scripts, so it always returned 0. And because we're always running this continuously deployed in the gate for verification, every job passed, whether it failed or passed. And a couple of projects managed to break themselves in the 3 hours it took us to catch my mistake. So that was a pretty good motivation for actually testing what we were doing. And it's since grown significantly. We started with 4 tests, unit tests, just testing that wrapper script at the end of Havana. And at the end of Icehouse, we had over 500 unit tests. So we're starting to increase the quality in the quality assurance program. It's a bad pun, I'm sorry. So now I'm going to talk a little bit about some of the cool features we have in Tempest. One of them is parallel Tempest, which is something I spent a lot of time on, and a lot of time working with Robert on getting Teststar to do what we needed to run Tempest in parallel. But before basically the Havana release, we were running all the Tempest tests serially. So we had, at that time, I think it was about 900 tests only. We were running those one at a time, one in a single thread. And we realized that was slow and not sustainable for our runtime limit of about an hour at the gate. So we said, well, the simple thing is to run the tests in parallel. We can do that with unit tests. There are interesting synchronization issues when you're running multiple API requests at the same time. So we had to get around those. But the other thing we found when we switched to parallel was it's actually more closely simulating a real load on the cloud. in your OpenStack deployment, you're not going to have a single user sitting there in a loop hitting it one request at a time. You've got hundreds of users hitting the API all at the same time, and you're going to have interesting cross reactions because OpenStack is a distributed asynchronous message passing architecture. So you're going to have all sorts of non-deterministic behavior pop up. And that's something we've actually found has hugely improved the quality of OpenStack. The fact that we're running 4 to 8 threads when we verify Tempest in the gate, as part of the gate, we've shake loose tons of race conditions in all of the projects and fix them and make things more stable. And granted, we have hundreds of race conditions that we know about today that still aren't fixed, but the fact that we can find those means that Parallel Tempest is doing a huge job in improving the quality of all the projects. And as I said before, the speed is also greatly improved. I mean, we were pushing an hour with less than 1,000 tests before we turned it on. After we turned it on, we're running about 2,300 tests in 40 minutes to an hour. So it seems like it's slow for a test suite to take that long, but we're actually doing lots of things, like spinning up 80-second level virtualized guests as part of a test run, for example. We're doing real work because we're not mocking anything. It's all functional testing with OpenStack actually running. The other thing which we started at the beginning of the Juno cycle was branchless Tempest, which is a little confusing, but basically we got rid of the concept of releases in Tempest and stable branches. So before, when the OpenStack project released, we would release Tempest and we'd say, okay, after this point, everything here is the stable, it's a Havana branch, so this is stable Havana Tempest. And then we'd start again, and then when the next release happened, we'd say, this is a stable Icehouse branch. And we'd go like that. And then if there were fixes we needed to backport, we'd backport them. But what we figured out was that by doing that, we weren't actually verifying the API was consistent between releases, because we'd be running the stable branches against the stable branches, the stable branch of Tempest against the stable branches of the projects. And there wasn't actually running whatever Tempest was in its current form against both the old and the new. So if there were bugs in Tempest in the stable branches, then we wouldn't catch the fixes to that necessarily unless we backported it, and we weren't very good about backporting. So what we decided to do was that from Icehouse forward, there's only going to be a master branch for Tempest. And this will ensure that the API is consistent because we're running the same exact tests on master as we are on stable Icehouse. And moving forward, stable Juno will run on master Tempest as well. This is something that's actually gotten surprisingly controversial, the fact that we want to ensure that the API is consistent between releases. A lot of people don't understand that there aren't backports anymore in Tempest, and that if you want to fix bugs, you have to backport them. So if there's a breaking API change for, I think the most recent example was Keystone. They started deploying under Apache, and the head response code on success was different when you run under Apache than it was under whatever the other WSGI stack was. And to fix that, they needed to backport changes to Icehouse because otherwise it wouldn't land because the API wasn't consistent. It wasn't consistently broken, I should say, between the releases. So they had to fix it, and to fix it, they had to backport it. And what this really does is makes end users' lives happier, or end users happier because the API is the API, and it's not the API of the random Git hash that you're running, which was a problem. Like, for example, if Rackspace Cloud was deployed, they all continuously deploy, but if they were running Icehouse and HP Cloud was running Havana, the APIs weren't consistent. You wanted to write code to talk to both clouds. There was no guarantee they'd be the same. So by doing this, we're ensuring that things are consistent between releases. And it's not just releases, but any point in time. Well, I guess that's the end of the slides. I thought there was more. So those are the links. I assume the slides will be posted at some point, but it's a link to the Tempest repository and Tempest documentation, both of which have far more details of cursory glance of everything I've been talking about. And if you ever want interactive help, it's obviously the OpenStack dev mailing list, and we all hang out. Everyone who works on Tempest hangs out in the OpenStack QA channel and Freenode. Just feel free to ping us if you have any questions. So it was the last slide. Are there any questions?